Hey, what's going on, guys? Xiangqi here. Last video we've implemented a logic to save computer's group of stones by putting the stone to the only liberty left. And in this video we'll try to teach it to take some defensive actions. So in the case if it has two liberties, then it would need to pick up one of those to if it puts the stone there, it would eventually result in more liberties as opposed to the number of liberties it would result if it considers the other one otherwise. So a bit of a tricky to talk about this, but it's much easier to actually explain, much easier to write some code and to show visually how this works. So without further ado, let's actually start. Here I want to grab this entire save own group because the code is going to be fairly the same, and yeah, we also want to comment this out just like the previous one so we can focus only on the current logic we're working with. So here we want to not to save but to defend own group. So init piece match own group, same thing. Count liberties for own group, same thing. So here we say if group has two liberties, then we want to take the defensive action. So here, instead of this, we don't have the single best move here. So instead we want to do a little bit different thing. So here we want to find the best liberty. So the best liberty is going to be evaluate and the current square we have. I'm sorry, obviously not the square, but the color. So evaluating for a current color, because we have the liberty to evaluate we already have after this count actually worked. Okay, so we're going to be looping over these liberties to figure that out. But since this exact piece of code, what we will have within the eval function, and probably it's not the best ever way to, let's call it evaluate instead, evaluate, to avoid using the having the conflict with the existing Python eval function. So evaluate, and this exact logic that we'll write for evaluate function in this video in particular would be used for surrounding the opponent stones as well. The only difference would be that it would be considering instead of looking for own group, it would be looking for opponent's group and trying to reduce the number of liberties in exactly the same way how it tries to extend them for the own group. So best liberty evaluate color, and this evaluate would be returning the best liberty. The best move would be equal to best liberty in this case, and here the defend move is going to be equal to the target square. Okay, so here we're going to be considering the defensive moves, and now let's go and implement our evaluation function. So find best liberty to extend or attack or surround. Okay, so def evaluate, and it takes the color. Right, so we have a couple variables here. So the best count goes first. So this is the count of liberties. Let's say max number of liberties found. So this is what the best count stands for. And the best liberties, the best liberty itself. So best liberty, if it doesn't find anything better, then by default it would be considering the very first liberty available within the liberties list, right? So we already have that list been generated since we previously has been looking for has been counted and didn't yet restore the board. So here so defend own group, so we did count, so this has generated the list of liberties, and we didn't yet restore the board here. So at this point when we call in evaluate, we already can work with a global list of liberties, so we are making use of that here. Okay, so by default the best liberty is the first liberty, so we don't find anything better there. and eventually we want to return the best liberty. Okay, and return best liberty. Now you might be wondering how exactly we're going to be doing this, like finding the best one. So first we need to loop over the liberties within the list. So I can simply say for liberty in liberties, like this. And now we're gonna be considering some probing moves. So we'll put a stone on board, then call count, and see how much liberties that would result. And if that exists, if that is the number is bigger than what we currently have, then we'll consider it. Otherwise, we don't. It's very simple, similar to what we have been doing in the eninge algorithm when we've been doing with the chest. So here, I just want to put stone on board. And hence it's not a real move. We don't need to handle the capture, so I'm not using the set stone here, but I just want to say the board indexed by the current liberty is equal to the color. So we just put this stone on board, and then we want to remove stone of board, stone of board when everything is done. So board indexed by the liberty is going to be equal to empty, so we want to remove. And the most interesting thing happens in between. So count new liberties here after we did put this stone. So I just want to say count, and I want the current liberty. And again, like this liberty is the coordinate, this is the square index, and just to make sure it works, we need to make sure that there is a stone, because otherwise the count is not going to be working. So count the liberty, and for a given color, and now let's say found more liberties, found a better move. So if the length of the liberties, and this time the liberties are getting extended, is greater than the best count. Okay, and this is important. Want to, and it's not detect edge, so it's not on the edge. So this is an extension that I think that might be worse. To check out this liberty that we have, the current one. So in this case, we want to set the best liberty to the current liberty, and the best count is equal to the length of the resulting number of liberties, the length of the liberties. And that's pretty much all that we need to do here. Okay, yeah, one last thing not to forget to do, we obviously want to restore the board. So restore board, and this is pretty much all about it. So if I did everything properly, then in theory and hopefully in practice as well, this should now start defending its own group of stones. So let's have a look if that is the case, basically. So just start a new game here, detach the engine, manage, and I want to update to the current file. All right, so Wally plays as white, and let's have a look. So a random move so far, well, that's okay. So let's just, okay, target square at the defend. You must be kidding me. Target square at the defend, wondering. Oh, this one. So here, define not the target square. This is this should be the best liberty as well. Okay. Yes. So one more time. You don't save. Set as white player. Just play somewhere, yeah, in the closer to the center. So at the moment, when I put the stone here, there would be only 2 liberties left here, and well, in this case they are fairly equal. So that's kind of okay. And you see like it extends now. Okay, so now it extends, right? Well, a little bit of a downside that sometimes it might result in the ladder, but it makes it really fun to play with. And for instance, like in this case, when all the features are available, it's not going to continue the ladder. Instead, it would break the ladder by capturing this stone. So it has this sort of a logic has its own pros and cons. So the pro is that actually trying to extend the group, which is great. So it tries, you see like it extends the group, you see like it extends it even more. Now it's okay. So okay, was it yeah, this was still the random one. And now this is the defend move, so now it extends again. So yes, this is kind of quite interesting logic. So actually not only trying to save the group, but actually whenever there is less than 3 liberties left, it tries to extend to the position where it gains the maximum number of liberties at the very end. So hope that makes sense. And in the next video, we'll apply exactly the same algorithm, but for the opposite purpose. So we'll make it surrounding our own groups of stones. So computer would be trying to surround users' group of stone using exactly the same algorithm. This is it from my side, guys. Thanks for watching. Until next time, and take care.